Okay, so now that we've looked at chemical equations, we need to go to we need to learn this important skill of balancing our chemical equation, right? So I gave you this example last time, and actually of hydrogen and oxygen reacting to form water. Balancing a chemical equation is all about making sure you have the same number of elements on the one side of your chemical equation as you do on the other side of your chemical equation. Okay. Um, Again, in these chemical reactions, matter is not being created or destroyed. It's not like oxygen atoms are being poof out of nowhere, right? They're coming from another source. So in these chemical reactions, they always happen in this perfect balance. So for example, you can see that I have two hydrogens on this side and two hydrogens on this side. So far it's balanced. But if I look at the oxygens, I have two oxygens over here and only one over here. So what I would need to do is balance my chemical equation by saying that I not only, it's not one molecule of water that's generated in this reaction, it's two molecules of water. That balances my oxygens. Now, when I put that there, all of a sudden now I've made an imbalance in my hydrogens. So how do I get the total number of hydrogens? It's this 2 times 2. So this would represent 4 hydrogen atoms in this molecule, right? Or in this, two waters would be 4 hydrogen atoms, right? And if we think about it, we learned about Lewis structures before. If I just draw 2 water molecules, you can see that I indeed have 1, 2, 3, 4 hydrogen atoms, right? So I need to go back and balance my hydrogens by putting a 2 out front there. And that's how this balancing process is going to work. It's kind of like a guess and check sort of thing, where when you balance one thing, you might have thrown off everything else. And so you have to go back and double check. There's no one way to do it. I'm going to teach you guys some strategies that'll make it easier. But the bottom line is it's all about kind of guessing and checking and making sure that you have the same number of hydrogens, but same number of all the elements on both sides. So in this case, it's hydrogens and oxygens. So what I'm going to do last is just double check. Right now I have 2 times 2, 4 hydrogens over here, and there's no coefficient out front of that oxygen. So I just have 2 oxygens over here. Over here I have 2 times 2, so this is 4 hydrogens, and my 2 times my 1 oxygen, 2 oxygens. This is the main goal of a balancing. The fact that I have the same number of hydrogens and the same number of oxygens on both sides of my chemical equation. If that isn't the case, then your equation is imbalanced. All right, if I were to find out that one of these numbers didn't match, I'd have to go through and redo something to make it match. Okay, let's do another slightly harder one. Oh, the other thing I want to point out, another thing that you'll see in your chemical equations is what's called the state of matter. Oh, I erased it. So this was an L. Okay, that just shows you what form the compound is. So G for gas. All right, let's just go. S is solid. L is liquid. G is gas. And then there's AQ, which stands for aqueous. This is another way of saying a solution. All right, so this next example is a little bit tougher. So I just wanted to do this so that you guys could kind of see how my reasoning would be. First thing I'm going to do is just kind of go down the line and make sure that, try to sort of balance on the fly as much as I can. So starting off with the calciums. So first you want to identify everything on both sides. So this calcium over here, chlorine over here, sodium, and then phosphate is a polyatomic ion, but I can actually treat it as one whole thing, because the phosphate isn't going to change from one side to the other. It's still PO4 and PO4. So rather than worrying about the phosphate and the oxygens individually, I'm going to keep track of the PO4 all by itself, right? So just make sure that I have the same number of PO4s on either side instead of worrying about the same number of oxygens and the same number of phosphoruses. Okay, so looking at calcium, I have 1 calcium over here, but I have 3 calciums over here. So I'm just going to start updating my coefficients. So I need to put a 3 out front here. Moving on to chlorine. So now I have 3 and 3. And I might have to continuously update that number. I don't really know. You're not going to know until the very end when everything matches. So now going down the line, I have 6 chlorines over here. I have 1 chlorine over here as it is. So I'm going to put a 6 out front, and that will update that. Looking at my sodiums, I have 3 over here and 6 over here. Well, I can square that off by putting a 2 there. That will make it so that I have 6 on both sides. And again, I'm going to treat that phosphate all together. I'm not going to break it up into phosphorus and oxygen. Over here, I have 2 phosphates. And over here, I have, 2 phosphates. So I have 3 calciums on both sides, 6 chlorines on both sides, 6 sodiums on both sides, and 2 phosphates on both sides. So this is a balanced chemical equation. All right. So yeah, just some other tips. So first of all, focus, if you have an element that's all by itself, worry about that last. Okay, we're going to see this when we talk about combustion equations here real quick. But yeah, so for example, a compound like CO2, you would want to worry about that before worrying about the element O2. It's basically easier to do those at the end. Like I'd said before, treat polyatomic ions that appear on both sides of the equation as one unit rather than breaking them up into their individual atoms. And then always count carefully. This is an easy thing to kind of mess up. I will tell you, practice will make perfect, because it's something that when you first start out, it seems like it's very difficult and you're kind of like taking forever to do it. And then once you get the hang of it, you can just kind of look at it and it'll kind of all make sense. All right. But you do have to, it is tough. All right. Don't get me wrong. So I wanted to do this other equation here, just one more here. So if I'm going to worry about my individual elements last, really what I'm going to focus on is that polyatomic ion, although as it is, those are balanced. So one PO4 over here and 1 PO4 over here. So now let's look at the sodiums. I have 1 over here and 3 over here. So I'm going to have to update that with a 3. All right, that doesn't mess anything else up, so that's good. And then now I get to my hydrogens. I have 3 hydrogens over here and 2 over here, right? 3 over here and 2 over here. So this now puts us in a little bit of a tougher spot, because it's not quite as easy to see what coefficient I'm going to put here to make those square up. There's really nothing that I could put there. Well, actually, so how to think about it is the only number that I could put there that would make everything balanced is 3 over 2, right? 3 halves. That would make it so I have 3 hydrogens over here and 3 over there, right? Because I have 3 times the 2 down here, but then divided by 2. So that gets me 3. Okay, there's a problem here though. And that is, when you're balancing chemical equations, you're only allowed to have whole numbers as coefficients. So this right here is an illegal coefficient. It's not a whole number, it's a fraction. But if I get to this, I get to where my equation's balanced, everything's perfectly balanced, I just have one of these fractions instead of a whole number. What you can do is take your whole equation, take the whole thing and multiply it by 2. Because 3 halves times 2, that will be 3, so that will turn that into a whole number. And then I just have to adjust all my other coefficients as well. So what do I mean by take the whole thing and multiply by 3, or by 2 rather? I'm gonna try to crunch this. Move this off to the side actually. It means I'm going to take this 2 and I'm going to multiply it by every single coefficient in this equation. So it's no longer going to be 3, it's going to be 6 sodiums plus 2 phosphoric acids. I'm doing my double arrow again. And 2 sodium phosphates now gives me 3 hydrogen gases. Be good about my subscripts. AQ, AQ, solid. All right, so you see that how every single one of these coefficients was multiplied by 2. And that's how I was able to balance my equation, because now I have effectively just increased all of these numbers by a factor of 2. So 2, 6, and 6 on this side. And then same thing over here, 2 phosphates, 6 sodiums, and 6 hydrogens. So if you do get to a place where everything's balanced, but you have a fraction, that's a really easy situation to take care of. All right. This is a particular type of particular type of reaction called a combustion reaction, and we'll talk about that a little bit more later on. But the bottom line is combustion reactions are really easy to spot because they always have the same products, CO2 and H2O. All right. This is also sort of a tricky problem to balance because I have oxygen in both of my products. If it's in one of them, it's a little bit easier, but it's in both of them. So adjusting either one of those will change the number of oxygens. So this is a type of problem where waiting till the very end to balance your oxygens is going to be really beneficial. Okay. So let me just space things out a little bit better. C4H10. All right, and as always, I'm trying to figure out what these coefficients are. That is the problem with balancing a chemical equation. All right. So this is another strategy, sort of because there's oxygens all over the place, I'm gonna worry about that last. I'm gonna focus on the carbons first and the hydrogens first, and then I'll worry about the oxygens at the end. Okay. All right, so I have 4 carbons over here. As it is, I only have 1 over here, so I'm going to put a 4 here. Now I have 4 carbons. Hydrogens, I have 10 over here. As it is over on my right-hand side, I only have 2, but if I put a 5 as my coefficient there, now I have 10. Okay. So now that I've balanced, so if I'm only paying attention to carbon and hydrogen, they're balanced. Right? I have 4 carbons on both sides and 10 hydrogens on both sides. Now I can worry about the oxygen, which I've put off. So this would be 4 times 2. So I have 8 oxygens in CO2 and 5 oxygens in water. So this brings me to a total of 13 oxygens on the left-hand side. And on the right-hand side, I have, no, I'm sorry. I always mix up my left and my right. I have 13 oxygens on the right-hand side. On the left-hand side, I only have 2. So again, there's not really any whole number I can use here to adjust this value for oxygen, but I could do 13 halves, 13 over 2. that would make it so that I had 13 oxygens over here and 13 oxygens over on my product side. Okay, but then what are we going to do? Again, let's remember, what do we do when we have a fraction? Because again, we have to have whole numbers. I'm just going to take this whole thing and multiply it by 2. So my final answer would be 2 C4H10s plus 13 O2s give me 8 CO2s and 10 H2Os. This is my final balanced chemical equation, because again, I can kind of update all my values by just multiplying them by 2. So 4. Same thing over here. Everything got multiplied by 2. Now this is 16 oxygens plus 10 oxygens would give me my total of 26. Okay, so that's how we balance our chemical equations. All about making sure we have the same number of this particular element on the reactant side as we do on the product side. And again, it's a reflection of the fact that matter is not created or being destroyed in this, just kind of reorganized. So if I didn't have 13 oxygen gas molecules, I wouldn't be able to make 8 CO2s and 10 H2Os. The other thing is, that's like always the ratio that these are going to be reacted in. I'll always have 2 of these C4H10s reacting with 13 oxygens. It's a perfect ratio. All right, so now let's write the balanced chemical equation for the aqueous reaction of barium hydroxide and perchloric acid to produce aqueous barium perchlorate and water. Okay, perchlorate is one of these polyatomic molecules I told you that you didn't have to worry about. So yeah, you might not know the structure of that without having to look on that cheat sheet, but nonetheless, this is the type of reaction. Assuming that we knew what everything was, you want to be able to translate these written statements into chemical equations. So barium hydroxide. So first, okay, so perchlorate you wouldn't know necessarily because I told you didn't have to memorize it, but hydroxide you would know. That is one of the ones that I told you should have memorized. So that's OH minus. Barium hydroxide, now I got to go to my periodic table, get rid of my 7. I find barium. Barium lives in the second column, so that means it has a 2+ charge. So barium hydroxide is Ba2+ and OH minus 1. So if I'm going to make my compound, barium hydroxide, you can see how a lot of the skills that we've learned up until this point are all kind of come into use here. When we get to next chapter, we're going to be using these balanced chemical equations in stoichiometry, in these math problems that we've been learning, right? Like converting from grams to moles, that type of thing. So all of this stuff is, you can't forget what we've done previously because it's going to be used at the later portion of the course, right? So this is a good example. If you don't remember how to form these ionic compounds, this would have been something that we discussed all the way back in chapter 6. I don't remember what chapter it would have been. But anyway, when we were talking about ionic compounds and naming ionic compounds and the molecular formulas for ionic compounds, these are these skills that we would need. Perchloric acid, again, I would forgive you if you didn't know. Perchlorate is ClO4 minus 1. And it says that this is an aqueous reaction. So this is aqueous, and they're going to form barium perchlorate. So now we have to make Ba and ClO4 minus 1. So hopefully you guys can tell me what the molecular formula of that ionic compound would be. Ba, ClO4, 2. And it says it's aqueous barium perchlorate. So this is still AQ plus water, H2O, which is a liquid. Okay. First thing I'm going to do is go through and sort of identify what's what here. So barium appears on both sides. Again, my polyatomic ion, the perchlorate, I'm not going to break it up. I'm going to treat it as one unit. That's on both sides. And this one's a little bit tricky in that it's not quite as obvious where the hydrogen went and such, because this hydroxide and this hydrogen are going to combine to form water. So because that's a little bit less clear, I'm going to focus on everything else first. Let's make sure the bariums are balanced, make sure the chlorates are balanced, and then we'll go back and worry about the hydrogens and the oxygens. So barium, as it is, I have one barium on my reactant side, one barium on my product side. Cool. I have one of these perchlorates on this side, but I have two of them over here. So I'm going to go ahead and balance that by putting a 2 out front. All right, so I notice how I just kind of ignored what I thought was going to be the hard part until the end. Now I'm going to go back and make sure that everything's actually balanced. I have 4 hydrogens over here. Well, actually, let's do oxygen first. I have 2 oxygens over here. I have 1 oxygen on this side. So I'm going to balance that by putting a 2 out front. Now I have 2 oxygens. Now I have over here 2 hydrogens in the barium hydroxide plus the 2 hydrogens in the perchloric acid. So that's 4 hydrogens. And I have 4 hydrogens over here because I put that 2 coefficient out front. So this will be the balanced chemical equation. This is the complete balanced chemical equation equipped with these little subscripts indicating the state of matter, as well as, very importantly, the coefficients that lead to our balanced chemical equation. Notice that when it's 1, you don't put it, right? We just leave it blank, similar to when we do our molecular formulas.